Tell me how you're going to set this up. John, how would you set up this one to find the percent solution? 85 milliliters of ethanol. Over what? Why are you saying 250? Why are you not adding? Well, you're right. Yeah, you're right. Tell me why you're right. How is this phrased differently than what we were just talking about previously? It says 85 milliliters of ethanol is 2A volume, right? So diluted 2A volume means this is the total volume of 250 milliliters because it's saying diluted 2. It's not saying 85 milliliters of ethanol plus or added to 250 milliliters of water. That would need to be summed, right? That would need to be added, but it's expressed a little differently here. So that is our total volume of 250 milliliters of solution total. And so if that is the solution total, we're going to take that information, 85 over 250 times 100. What's that percent? Jackson, what's that percent solution? Everybody should be calculating because that will actually help us get to our homework. Number 1 through 8. 34% is what they say. Is that right? Yeah? Sounds great. Okay. So these percent problems are very easy. That's why I saved these for today so we can knock these out. There's a, can you maybe guess, what would the units be if I was talking mass percent, not volume percent? Grams of solute over grams solution. It would have to be the total thing, right? Not just solvent, but solution total. Oh, and this is why you'll see, have you guys ever seen different bottles at Walmart, 70% isopropyl alcohol versus 99 versus 3% hydrogen peroxide, all these percents that are written, they actually have a reasoning behind them. It's because that volume to volume percent we just did. So if you're talking mass percent, you can see the only difference here is that it's grams over grams, and that again, it's just total here. So this would be sometimes written in a problem where you have a solid solute and a liquid solvent, but they would give it to you instead of in milliliters in grams. So that would be mass to mass. And occasionally, so we did volume to volume, we did mass to mass. Sometimes you'll see mass to volume like this. And so you just have to go with the flow. If it says to do mass to mass, look for the grams solute, look for the grams total, divide. But this is the only one that doesn't make as much sense because the units don't cancel. So this would be like grams over milliliters times 100, and you'll have one of those in your problem set. So if it says to do that way, then stick with it. Good with mass percent or all percents? What's generally just the schematic of how to calculate percent? So part over whole. That's it. Okay, moving on. Told you mass percent is really easy. All right, so what we didn't do yesterday, we're going to go ahead and do this. All right, look on your worksheet that I gave you. This was on the solubility curve one. Your lecture. Go ahead and do number 7 and 8. Talk to people around you. Take about 4 minutes maybe. 7 and 8 to work. 7 and 8. It's the concentration problem practice. Concentration problem practice. It's in the upper right-hand quadrant.
Which number?
7 and 8. Use your notes as needed, use your people. You notice that we have a quiz after this, so make sure that you're working here. Really play with the mold. Wait, are you? See what I'm saying? I'm not writing the word right now. I'm writing down my givens. Let me look at my work.
Or this one's the.
Yeah, this process on the
Like, so they give you. So there's two boards, right? So I got like, the empty them.
Let's talk about number 7 real fast. Okay, so number 7 says to describe, which you know to me is going to be like a sentence describing how to prepare it. Well, you did this yesterday in the lab, but before you even started telling me how you're going to prepare your solution, you had to figure out how much stuff to put in it, right? There's a quantity involved on this one. And so I think Jakari and John told me, you guys started telling me how to do it. There's 2 ways to do it. Given these 2 pieces of information, there's only one thing you can do with them, right? Solve for what? X, which is moles in our case. So a lot of you guys really like this proportion. So I saw a lot of you guys going, okay, 0.025 molar, which is moles per liter, because molar is moles per liter, is equal to X number of moles over what? 0.1, right? Do not put 100 milliliters there because that's not the same unit. So you cannot set up that proportion. So 0.100 liters. So you cross multiply divided or just did 0.1 times 0.025. And that's what I usually do. I usually go M times V gives you moles. You guys wrote this down on your notes a couple days ago. Remember seeing that? This is the same thing as you setting up a proportion. It's just I'm going straight to the calculation phase of it. So what is X? What's our moles here? When you multiply 0.025 molar times 0.1. 0.0025 moles of, name this for me. Sodium carbonate. Still got it, people. Okay, so we got our moles here, but I can't measure out moles, right? What do I generally measure out? Grams. So I'm going to need to get the mass of this, which would mean me doing what? Looking at the periodic table, getting the molar mass. Okay. So what is the molar mass of this? 105. So 106 grams approximately of sodium carbonate. So I'm taking the moles and multiplying it by 106 per 1 mole. 106 grams per 1 mole of sodium carbonate. So how many moles is that? I mean, sorry, how many grams is that? That times 106, huh? 0.26 grams of sodium carbonate. Okay, so now we've got a number to work with. So yesterday I went around the lab and I was like, okay guys, got your numbers. What are you going to do now? What kind of equipment were you using? The volumetric class. What volumetric class do you think we need in this scenario? A 100 milliliter one. Okay, so when you describe it, all you're going to do now is just go, okay, take what? Okay, so take 0.26 grams of sodium carbonate, add to what? Well, add to what piece of equipment are we going to add that to? To a 100 milliliter V flask. So a V flask is a volumetric flask. Okay, then what? How much water? Not straight off the bat. You did about halfway, right? So take 0.26 grams, add to 100 milliliter or 100 milliliter volumetric flask, fill halfway with water, swirl, and then fill to etch line. Or the line, whatever you want to say. So I think once you got to the point where you're like, oh, I got to calculate something, then you would know that, oh, I got to take that number of grams I got, add it to the volumetric flask, swirl like you did yesterday. So that's helpful because it helps you think about reflecting what you did, walking through yourself through the process. So can you do this on your test? This test is Thursday. It's cumulative. It's thermochemistry, which I'll hand back to your class today, and some of the stuff we've been doing with concentrations like this. Okay, so that's what I want you to be able to describe. And then for the second one, I think we all saw you were using M1V1 equals M2V2. Which was the one you were solving for? V2. So then you said your V2 is questionable. It said making a 120 milliliter of what molarity? 4.0. And if you want to list those as M2, that's totally fine. It's just these two things needed to go together, either as M1V1 or as M2V2. It doesn't necessarily matter. But the stock solution was what? 16 molar? So you have to take 16 molar and dilute it down to 4 molar, but you need 120 milliliters of it. So when you solve for V2, you should have done M1V1 equals M2V2. V2 is equal to M1V1 over M2 by dividing M2 out of the system here. And so when you plug in information, V2 is equal to 4.0 molar times 120 milliliters over 16. And you can do this in your head. What's 4 over 16? 1/4. What's 1/4 of 120? 30. So a quarter of 120 is 30. Okay, so then you would say 30 milliliters. You take it from a stock solution, put it into a what piece of equipment do I put it into? Volumetric flask, and add water until where's the next line at? Our diluted volume, okay? So you're going to take this, add it to your volumetric flask, add it until you reach a total of 120, which is where the next one is. Okay, I'm feeling good about life. You guys got all your stuff, your notes, your calculator, piece of paper, phone? I'm going to leave this open notes. I'm going to turn on the soccer tip quiz in a minute. It's 3 questions, okay? So I'm really excited to talk about.
I get one more.
Alright, so you have open notes. Please use your notes. If you take good notes, then you will be rewarded. Let's do this, people. Not open person, just open notes. All right, Socrative means go to socrative.com, student login. Enlo is the classroom name. And it shouldn't take, it's 3 questions, it shouldn't take you more than about 6 or 7 minutes. If you can't get on a phone, then I have desktop computers for you. After that, you guys are going to start writing down this information for me. All right, darlings. Last big topic for the day, for the day and the year. really appreciate making ice cream bar, okay? So make sure you make a note to yourself, write in your hand, sprinkles, chocolate syrup, whatever you want, honey, Oreos, those little things you put in the side of ice cream, like at a soda shop, those wafer cookie things. You know what I'm talking about? No, wafer cookies, sorry. I'm just saying, okay? All right, so tell me, I know this is really, like, this is going to be a hard one, guys. What is the boiling point of water? I really like when people say 100. 100, I can't say it. I'm not good at fabulous math. Okay. 100. Okay. So boiling point of water, H2O, is we say 100 degrees Celsius. Who has ever cooked spaghetti? Or noodles? Or pasta of some sort? Okay. Some of you guys need to learn how to do that before you were an adult. Okay, so what you should do, first of all, you pour water in the pot, you start to boil it, you put the pasta in. You turn around, you're playing with the daughter or something, you come back. This is my experience, okay? Water is boiling over. It's like shh, shh, shh. So it's making all those noises. So what do you do to stop it from boiling over? Okay, turn off the oven. Give me some chemistry behind it. Stir it, okay? Who's ever put salt in their water to stop it from boiling? Who just put salt in it? Okay? So some of us, okay, we know the magic here. What happens is when the water's boiling over, a lot of times people will just put some salt in there and they'll just dash it over the top and it stops boiling. Why does it stop boiling? Well, it's not because there's more stuff to boil, actually. It's because okay, so it takes, say what you're saying? Okay, so maybe it's a difference in their specific heat capacities. So it's not boiling at what the temperature was it was previously boiling at. What was it previously boiling at? 100, right? Actually, what happens when I put the salt in, it actually increases the boiling point of water. So maybe the boiling point of water is like 102, 103, okay? So the new boiling point for salt water, this is like sodium chloride, is 102-ish degrees Celsius. So it's not boiling because it's not 102 degrees Celsius yet. You just boiled it at 100, put your salt in, and it stopped boiling because it's not up to temperature yet at which it should boil. Well, why does that happen? Really what's going on is water likes to dissolve things, right? It likes to dissolve salt. So instead of getting enough energy and popping out of the top of the surface area, it instead takes its energy and puts it into the dissolving of salt. So it's like, I can't boil, I gotta dissolve this thing first. So it can't boil off because it's interacting with salt. It's going through hydrogen bonding, dipole-dipole forces, and it's just actually dissolving the salt. So there's another reason too. It's based on the vapor pressure lowering. And I'll get to that in just a second. But basically the big idea here is that a pure solvent has a property. When I make it a solution and put a solute in a solvent, I then can change that property. So they're called colligative properties because they're not pure solvent properties, they're physical properties of mixtures. And the mixtures, it doesn't necessarily matter what you put in there. It depends on the number of particles that thing breaks into. So sodium chloride, right? We all know what sodium chloride is. You put it in your water yesterday. You measured the conductivity. What was the difference? What was the magnitude of the conductivity of like the saltwater solutions you made? Approximately. 37,000, right? 37,000 microsiemens per centimeter. What was the conductivity of water, just pure water? So closer to 0, right? So like 100 ish. It really should have been like actually 0. Deionized water means it doesn't have any what in it? Ions, right? It should have no ions. Our water is not 100% deionized water because we have this little distiller that doesn't work as well as it should. But the salt, why does it make things conductive in solutions? This is what's happening. And draw this out for me. This is called dissociation. So if something is going to dissociate, it's going to take its solid form, which in this case sodium chloride. It's going to ionize. Well, what do you think it breaks into? Using your immense knowledge of chemistry. What does it break into? Sodium ion, because it's ionic, right? And chloride, right? So chlorine ion, which is chloride. Okay, so how many particles does it break into? 2. We call that the I factor. I is the I factor, and I factor is 2 in this case because there are 2 compounds or ions that it breaks into. The I factor has another name. It's named after a person, the Van 't Hoff factor. Van 't Hoff factor. So let's try this again. Let's do it with calcium chloride, though, in this case. Calcium chloride. What would the I factor be for that? Let's write out the dissociation like we did here. Calcium chloride. I'm ready when you are. CaCl2, because calcium's got 2 charge, drop it down. It's going to ionize into what and what? Ca with a 2+ charge and Cl with a 1-. But how many chlorines are going to have to be here to balance these chlorines? 2, and that 2 does not become a diatomic 2, it becomes a coefficient 2. So this is the dissociation of calcium chloride. How many ions remain at the backside? 3. So 1 + 2 is 3. So the I is 3. So what you're seeing is that different solutes break into different number of particles, and that's why it says up here, properties depend only on the number of particles, not on the specific identity. That is a multiple choice question I guarantee half of you will miss because you didn't star that, say on test, this right here, that what is a colligative property, what controls it, is the number of particles, which is the Bantoff factor. Okay, so that's good that we got that down. The 3 properties that we are going to talk about today are boiling point elevation, which is why I told you that salt water boiled at higher temperatures, like 102 versus 100. Freezing point depression, so we're going to call that freezing point depression, meaning lower than what it should be. Boiling point elevation means increasing. And these 2 are actually controlled by the vapor pressure lowering. So who was my atmosphere when I was the boiling water and you're pushing down? There's something in the front. Jack, were you my boiling water? Were you with the pressure pushing down? SJ, he's like, I've forgotten my memory. So SJ was the atmosphere. He's pushing down. Well, if the atmosphere is pushing down on the boiling water can't boil because it can't vaporize because the atmospheric pressure is really high. So what do we do when we put this stuff in here? These solutes in here. Here's what, I may actually have a picture on the next slide. Here's what's happening. The pure solvent's just vaporizing. Well, the boiling point, the actual point at which it boils, is when the atmospheric pressure, or P of atmosphere, equals the pressure of the vapors. So if that's the case, that's when it's going to boil. Well, when you put stuff in there, when you put solute in there, that's the little red particles here, here, and here. What did I tell you the water started to do with that? Well, the water stops behaving normally. What does it start to do with the solute? So it's to dissolve it, right? And so it's interacting. It's I'm not going to vaporize. I'm going to instead interact with this. So this interaction with the solute limits vaporization. And if we limit vaporization, it's never going to boil. So what we've done here is we've lowered the vapor pressure, and that's why it's called vapor pressure lowering. So that's kind of helping you see what the vapor pressure lowering standpoint is. We won't actually calculate anything with that, but does that make sense that the stuff in here interacts with it, it limits the vaporization? It's interacting so the water is just by itself not going to evaporate. Yay or nay? Kind of you're okay, we'll work on that one some more. That one's actually one of the least important ones because we won't be calculating with that one right now. These are 2 examples, or 3 examples, for freezing point depression. Okay, so these are examples of where do we see freezing point depression in real life? We see it on the roads when we put ice out. We put ice out. That would be a cruel trick. Okay. We put salt out on the road so everybody can come to school, right? Life goals, get that education. So we do this because the water in the roads naturally freezes at what temperature? 0 degrees Celsius. Naturally, the water has a normal freezing point of 0 degrees Celsius. So when I put salt on the roads, what happens is you guys remember how water organizes itself to form a solid? How does it freeze? It makes a shape. The hexagon, we saw it in the video with the fish. You may not have actually noticed. Okay, that one video we watched 2 days ago. Okay, so water organizes itself in a hexagon. Here's water. Okay, so great. They're interacting through hydrogen bonding, and there's a big air gap in the middle, which makes ice more dense than water. Less dense than water, that's why it floats, right? So if that's happening, it's going to freeze really easily at 0 degrees Celsius. But then you allow this intruder in. I can't find my red pen. I'm very distraught about this. No, I can't find the green pins on top. Because when I pick this up, it's red now. Okay, I've lost a pin. Don't know where it is. Okay, well, anyway. So this guy likes to freeze in a hexagonal pattern. When you start exposing salt or any other ionic compound to this, it's like homewrecker getting up in here, cannot get together, and there's salt everywhere, and it's breaking up the ability to hydrogen bond. So that can't happen. So if that can't happen, is it going to freeze? Is it going to turn solid? No. It's going to have to get super, super, super cold for this organization where the water was oriented to get back together because they need to slow down and then start to bond together. So it's going to get like, I don't know, negative 10 degrees Celsius. Does it get negative 10 in North Carolina? Heck no. So guess what? We will always go to school unless there's shady areas that don't get ice. I mean, don't get salt. So generally, the freezing point will depress quite a bit. And that's when it would freeze, never at 0 degrees Celsius because the salt gets in the way of the crystallization process. Okay, making ice cream. We'll see that tomorrow. And then antifreeze. This is in your car. Do you want your radiator to freeze? No. So we put stuff called ethylene glycol. Ethylene glycol into our radiator. And it's got lots and lots and lots and lots of ions and solutes in it. And so it depresses the freezing point so that our cars will work in the winter. And then separately, we actually put, it actually helps with, it's called antifreeze. But it helps stop your engine from also getting too hot. So it increases the boiling point because if the antifreeze starts to boil in your radiator, your car would explode. Okay, it would blow the radiator. So we try to have a one solvent that can go either way: increase the boiling point and decrease the freezing point. And then this is our example from earlier: increasing the temperature, which is good. Yeah.
Why is it when you're at a restaurant and you have a napkin and you put your cup on top of it and you put salt, it doesn't stick to the napkin anymore?
Because the napkin it's made of cellulose, which is plant fibers, cell wall, cellulose. Remember this from biology? You're like, cellulose? Who had me for biology? Okay. So cellulose in the plant walls. Cellulose has little OH hydroxyl groups that's sticking off the side of it. So hydroxyl groups have these OH groups, and they're polar, and polar like each other. So the water that's collecting in the glass attaches to the hydroxyl groups, and so it sticks. When you put the salt there, it stops the interaction between hydroxyl and the water. Good question. Okay, let's do some calculations with this. We got some examples, we got some concepts under our belt. Start with writing this equation, and then read this up here. I want you to tell me what you think each of these variables are. I think you should write down a couple more things, but at least once you write that, and then read it, and then talk to your group about what you think each of these variables here mean. Emergency go, you can wait a couple minutes, we're going to finish this up first. I don't know, record a little further. Okay, I feel like you've had time to glance. Three things that are in this equation. So this information, we just talked about boiling point elevation, which means the boiling point increases by a specific temperature change. freezing point depression, which means the freezing point depresses by a certain temperature change. This is that temperature change. Delta T is what we're looking for. We've seen delta T before in MCAT, which is going to be including heat, masses, and specific heat capacities. This doesn't have any of those, so this is not something you should be able to confuse even remotely. Each of these factors mean three different things. K is little k, and it's talking about the solvent, first of all, okay? That is super, super, super important. The solvent is always the larger quantity given in a solute-solvent mixture, so make sure you can always recognize the solvent in a mixture, and it's called the Mallow blank point, so freezing point or boiling point, depending which one we're talking about here. So Mallow freezing point constant, and it's always referencing the solvent. The I factor we already named. What was that called again? Some guy's name? Van't Hoff factor. And that's talking about the number of ions, ions, that's easy to remember, that the compound the solute breaks down into. So if it's ionic, you simply ionize it and through dissociation, multiply your molality, molality, little m, by the number of ions made. Well, there's another way to say ionic. Generally, we can call those electrolytes or electrolytic. This is important. This is a definition. I think that you did like your reading that already, but I want to make sure we're clear here. Electrolytic solutions. Do they conduct electricity or do they not? They do. Okay, and it's because they have ions in them that are able to pass an electrical current from place to place to place to place to place. Do you have electrolytes in your body? Yes. How do you replenish them? Gatorade. Okay, so some sort of sports drink or something with ions. Why do you need ions in your body? Energy is a distant triphosphate. That's different, right? We can't use ions for energy necessarily. Who's taking anatomy? Anybody? Lame people. Okay, so you need ions in your body. This is important to know. I have to remember this, but I'll make this extra credit because this is important. Your neuroskeletal system. Neuro meaning brain, nervous system, which does go throughout your body, right? Skeletal system meaning skeletal and muscular, right? It's like neuromuscular junction is what it's called. Neuromuscular. This is neuron, this is muscular. How does your brain tell your muscles to move? Just signal. Your nerves send a signal. What do you mean by that? It's an electrical pulse, right? Down the synapse, the myelin sheath fibers, which are like fatty deposits around your neurons. Okay, so this sends a pulse down, which is an electrical signal. Where do you think the electrical signal is coming from? Ion differences. It is coming from your brain, but your brain, basically there's a channel here, okay? And so the nervous fibers are innervating a muscle. And as the neuron touches this little place on your muscle, it's going to make an exchange of sodium ions in and out, and chlorine ions in and out. Potassium ions, there's lots of different ions involved. And once they make that change, it opens up the channel. And once the channel is open, the electrical signal is then delivered to the muscle, which causes it to contract, or to move, or to do whatever your brain is supposed to do. So if you don't have these ions, good luck, nothing's going to happen. So that's why you have to replenish them, because there's no way for those things to make their signal known, because it's all based on the biochemistry behind it. It's all based on, is there a barrier? Basically, it's just diffusion. If you have a lot of sodium ions out here, and none on the inside of this cell or whatever we're looking at, if you have a lot out here and you open the channel, what are they going to do? They're all going to go in, and they're going to go until they're equal, right? Because it's diffusion from high concentration to low concentration. If they can go in, the signal is delivered. If they can't go in because you don't have jack out here, it's not going to happen. It's not going to send the signal. So that's why we actually do need to know a little bit about electrolytes. Yeah. It's based on diffusion. It's based on numbers of them. But if you don't have them replenished, and this site is going to be non-functioning because there's no way to deliver the signal, which would just be opening the channel for the ions to flow. And if ions don't flow, then the signal's not occurred. Yeah, that's it. We're just a bunch of chemicals. Yeah. Say again? Most likely. Yeah, nothing would work. You'd be a vegetable. Okay. Allergy done. Chemistry back?
So what happens if you go to coma or whatever?
No, that's something actually a little different. It's just non-responsiveness. Okay, so electrolytes, ions, and solutions. If I see the word non-volatile, covalent, non-electrolyte, these are three things that say or that mean or say the same thing. That means non-conductive, okay? And if they're non-conductive, then they're probably covalent. And if they're covalent, do they break apart in water? No, they do not. They might dissolve, as in the layman's term of water surrounding it, but they do not ionize. So we call that I of 1 because it doesn't ionize. It's always going to be remaining one particle. So that's how we get our different I factors based on covalent always being 1, ionic, we dissociate it, we add up their coefficients, boom, we got it. Now, these values here, go ahead and write these down because you're going to need these numerous times today. So the KBP stands for boiling point, and this is for water, okay? For water is 0.512 degrees C per millau. Millau, which is that molality thing. The KFP, which stands for FP, means freezing point, we 1.86 degrees C per millau. So what's our delta T unit here? Kelvin or Celsius? Celsius, because you don't see Kelvin anywhere in any of these units at all. So no Kelvin, that only goes with gases. Thermochemistry and solution chemistry revolves around Celsius. So this is only for water, and if you want to write down, I'll put them up on the board later, but those are the 2 pages in your book where you'll find every other solvent with their little constants as well, which you'll need on a couple of your homework problems. Let's do one more dissociation before we move on. Do that last one. What's the name of that last one? Calcium carbonate. Dissociate it. Tell me what the I factor is. I'll give you a second here. Write calcium carbonate on your paper, arrow, like this. Tell me what it would break into. Jackson, what you got? So calcium 2 plus, that's the charge of calcium ion, and good. I hope carbonate CO3, 2 minus. I hope nobody was a home wrecker and broke up carbonate. So if you were starting to do Ca plus C plus O, bad, shame, okay? Carbonate is a happy polyatomic ion, do not break it up. Anytime you have an ionic compound, it's only a cation and an anion, and we crisscross their charges, so do not make 3 or 4 or 16 ions. Make 2 ions, and then the coefficients are related to how many we have of each of these. There's only 1 calcium, so there's 1 calcium. There's 1 carbonate, there's 1 carbonate. What's the I factor? 2. What would be the I factor of this guy? Second? 5. How many aluminums would it be making? How many aluminums? 2 aluminum ions, which are 2Al3+, and so you're saying aluminum ion, there's 2 of them, and what else? 3 oxygen ions, because there's 3 of them there. So that would be an I factor of 5. Okay, let's go to a calculation, and I'm going to walk you guys through one of them before I let you guys do one by yourself. Okay, so what is the equation that we're going to be using here? Delta T is equal to what? Sorry, not formula. What's the equation for this? K-I-M. I replaced a teacher when I taught at JM. Her name was Kim, so I named this after her. They all hated her, but we used it. I have like a nice, like, something over here, one of those good. Okay, so question. How much will adding 6.25 moles of sugar decrease the freezing point of 2.5 kilograms of water? So far, this is the only thing I feel is important. Decrease the freezing point, though. What does that phrase refer to? Yeah, but what is this unit is looking for? The what? Well, what depression means to lower, right? Which means to change. Delta T. So this is asking a question, what's the delta T? Okay? And then how will this change the boiling point? What will the new freezing point and boiling point be? So we got a little bit to go, and then we'll get to all those questions. Let's start with just finding the delta T. What is the solvent here? Solvent. Water. Okay. So you're telling me, hey, let's just do the freezing point one first. Not K, delta T. delta T freezing point is equal to K freezing point IM. For the solvent, what is the K value? You wrote this down just previously. Right, where did I get this, guys? I had it on the board earlier, where the KFP for water was 1.86 degrees C per milliliter. Okay, what is the solute in this case, Alvin? Sugar, is that ionic or covalent? That's covalent, guys. If it's covalent, what's the rule? It stays together, so the I is 1. Okay, so I think you should first identify, is this solute ionic or covalent? If it's covalent, stick with 1, because it doesn't break up, and then if it's ionic, you got to go through a degree of dissociation. So the I here is 1. What does little m stand for again? Molality. And what are the units for molality? I heard moles over kilograms of solvents. Okay, do we have both of those? Yeah, we sure do. I'm not even going to calculate it. I'm just going to put it in here as a fraction. So moles were given for sugar, 2.65 moles. Oops. The kilograms are already given for water, which is our solvent, so we're good to go, plugging that directly into the denominator, kilograms of water. And this whole thing here is molality, right? Moles per kilogram of solvent. So that is molality, yes? Okay, and that's important for me to just recognize, because if I write it like this, I know that this means M, molality. Which of these units cancel? Molality and molality, right? Leaving us with Celsius, which is what temperature should be recorded as, right? Calculate real fast. Calculate. This really helps because you guys, we actually speed it this way. What you got, Carson? So delta T for freezing point is 1.97 degrees Celsius, right? Okay, if we're talking water, this means that water's freezing point depressed, right, this is depression, by 1.97. So what's the new freezing point of water? Negative 1.97 because you subtract. So what we did was new freezing point is equal to old freezing point, which is 0, minus our delta T value, which we got here. That depresses it, so subtracting it depresses it. That's a negative 1.97 degrees Celsius. Easy peasy? Yeah. That's just me saying freezing point, because then later on in the question it says how this changes the boiling point. It's just helping me understand am I talking about freezing point or boiling point, and it'll help you do your subtraction at the end. Yeah, I do, because I just want to, as redundant I know, but it helps me recognize I'm dealing with the freezing point constant, not the boiling point constant. Yep. All right, let's do the boiling point one now. What's different between this, the way we set it up here, and the boiling point? Different what? Okay, so the actual setup is 100% the same, right? KBP times I times M. So delta T is equal to, what's the K value for this one? 0.512 degrees C per milliliter. So that's our freezing point constant for water. I'm sorry, boiling point constant for water. I value, 1 again. Molality, same. It doesn't matter because, like I said, it's dependent upon the number of particles. And we're talking about the same scenario, so nothing else is changing here. What was that divided by that? 1.06? No, the freezing point and boiling point are two different starting points. And then boiling point gets elevated, whereas freezing point gets depressed. So they move into separate directions. So this is 2.65 divided by 2.5, that's 1.06, I think. So then everything cancels except for degrees Celsius. What is that? 0.54 degrees Celsius. Sorry, I'll stop there. All right, that's our delta T. That's our boiling point constant. And boiling point is elevated, so what's the new boiling point of water? 100.54, because we took our new boiling point to be 100 degrees Celsius plus our delta T. And delta T is elevated, so it's going to go above 100. Who feels okay with this? Delta T? KIM is long as you can recognize your information, you should be in good shape. Go ahead and do number 2. I can remember that I have to right. You guys get next. You never know if I have a quiz. So we up here, we subtracted 0, I guess right here, minus the delta gives the negative 1.97.
Wait, do you want to take your
Definitely, because look. All right, who's had the eureka moment yet? The eureka moment.
No, wait, actually, no.
Okay, keep doing what you're doing.
Oh, yeah.
Keep doing what you're doing. Finish up. All right, guys, I want you to listen to Carson to tell us a small discovery that was made mid-problem. Ready? Go. So what does that mean? So how does that influence the ability to do this question quickly? What's different? It's basically the same problem. I did this because I wanted you to think and read. And as you start to write it down, you're like, oh, I've written this before. The only thing that's different is this is a sodium chloride, which does break into 2 ions, so the I is 2. The moles were the same for the solute. The kilograms were the same, basically, for the water. So what was this? How was this different than the first one? It was simply doubled, right? So the first one was like 1.97, and this is 3.94. So again, colligative properties, it's truly based on the number of particles. So we went from I factor of 1 to I factor of 2. The delta T just multiplied by 2 because that was it. The particles doubled, the temperature change doubled. only because I set up identical numbers otherwise though. And the boiling point constant being the same, the I being 2 again, and the molality being the same, should have had approximately about a 1.1 or 1.09 degrees Celsius change for the boiling point. These would then be added or subtracted to the freezing point. Subtract, this would be a negative 3.94, and this would be then added to boiling point of water, which would be 101.09 degrees Celsius. So that would be a little higher than 100. So do you always think about, I think I'm trying to think ahead, but this really was just helping you to see this part right here. The greatest impact is always going to be for anything that's ionic or covalent. Ionic will always cause a bigger impact because it does break into I factors that are higher than anything that's covalently bound. Okay, so I think I'm feeling good. Let's look at the problems that you guys have. So look at number, we have about 20 minutes left. You'll get through most of these. These are going to be on the paper you need to be working from. Your lower left-hand corner, it says lecture problems, colligative properties, 1 through 8. Yeah. It looks like this. And then I'm going to put some constants on the board for you so that you can take a picture to utilize. Yeah, these will be easy if you work with a partner on it too. These are the constants right here, guys. Kf and Kb's for every other thing other than water. If it says solvent that's non-water based, that's what you will be utilizing. This is on your textbook.
We're gonna get this for our test.
Say what?
We're gonna get this on our test.
Yeah, I'll give you the constants. All this knowledge? What? All this knowledge? Nothing? No. Maybe that was on purpose. Is that on your solvent? No, it's not. Water is yourself. Why are all these people? You need to get in the zone. Yes, you can use again, but I need to see some progress. So you should probably at least get 6 of these in the next 15 I'll have to go check on them. Yeah. And then you skip. Methanol. Are you doing that? Yeah.
And when it be on negative. Negative or negative. Well, the it'll be gone. Where is this? I don't even know what that is. Carbon. Will they give us the, it's not, maybe that's one. And it's from the so I should hear. Yeah, the markers are like one on. Okay, so we use that. Oh. Yeah. Violet. Oh, that's freaking point. Yeah. Yeah, but that and then we're looking for it. Okay, so we have, yeah, we have. What we're looking for. That's yeah. Okay, so you could find 10.
Sorry guys, let me guide you a little bit more before I move on, okay? Whenever you are implementing delta T is equal to KIM, you have to talk to yourself. The K values for the solvent, if the solvent is always a larger quantity involved in the problem. And number one, it's water because it's 500 grams of water versus 100 grams of methanol. So the K value is the freezing point depression constant for water, 1.86. The I value is referencing, does the solute break up? So you have to talk to yourself, is the solute ionic? Then it will break up. Yes. How do you know if it's ionic? What's always involved in ionics? Metals and nonmetals, right? Or metals and polyatomic ions. If the I value will always be 1 for anything covalent, right? And how do you know that's covalent? Non-metal, 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 non-metal. This one is methanol, right? Which is C's, H's, and O's. That's all non-metal. So it has to have an I factor of 1. Molality is moles of solute, meaning you have to take your grams of methanol to moles of methanol, divided by your kilograms of solvent, which means the grams of water. Back that decimal up 3 places, you get kilograms of water. So always think about, am I talking about solvent or solute in these? This is going to be solvent, and then the top one is, the I factor is solute. And then the other one is the molality, which we've done. Continue.
Yeah. Yeah. I don't know if the first. Yeah. Like. What was it? Yeah, well, we're looking. Yeah.
Oh, benzene is, it's what killed the guy.
It's like, so for here, so what's two classes? I mean, right.
Yeah.
But still, we can kind of get that by myself. I'm also. We put the water just so it's. Yeah. So we need to change the process.
Class number 2, you guys just, you're not thinking, okay? So whenever, here are the answers, by the way. I'll keep these up here for you in a second. If number 2 asks for you to solve for molality or concentration in molality, it's asking for you to solve for Chem. Well, you should have everything else in that problem. You'll have your delta T given, you have your K because it's regarding the solvent, you have your I because it's regarding the solute. So how do you get M? You take delta T is equal to KIM, and then you divide by KI. Divide by KI, and M has then been isolated. So think about what it's asking for and think about the equation and see if you can go from there. I'll leave those up there for now if you want to take a picture. Answers to me are meaningless without work, so make sure you're putting your units and such, and then I'll scroll back up so you guys can see those. And then raise your hand if you still need it. I might just hand back tomorrow so we can review it tomorrow, actually. So, okay, I want you to focus with me. But not, no more bathroom breaks for you, man. Teal, no teal. I'm trying to be gracious. I realize.
It's just
Are you asking me the formula or the case?
Okay.
I have that.
All right.
I don't have.
Guys, listen before you go. Ready? We got another minute. 1 through 8 regards all colligative properties. Thank you. Colligative properties definitely in your CS 16 should be done before you make ice cream tomorrow. So please make sure you prioritize that so that you can participate. Tomorrow we are making, we're doing our colligative property lab, aka bake ice cream, first, and then we'll be working on our unit review afterward. Unit review will be going over anything regarding information on tests on Thursday, which is on the board here. Okay. Bye.